About 2 months ago, I decided to tackle the challenge of building my own robotic arm. With minimal robotics experience, it meant I had to make all the mistakes possible, overcome many design constraints that I set for myself, reprint way too many pieces on my 3D printer, just to finally get to where we are today. Throughout the whole process, I filmed a lot of it. Hope you enjoy as we go back down through the journey of me designing this and getting to where we are. My goals for this project was to develop an arm mechanism that has 5 axes of movement, an ability to have controllable, programmable and repeatable movements, Bluetooth capabilities for controllers to the arm, potential commercialization, EMG or hand gesture recognition control, and have the ability to incorporate new inputs easily, like a camera for motion tracking or AI training. These goals were very ambitious, but I thought I'd go all out in the hope that this project just achieves at least one of those goals. And if we hit more than one, then that's just going to be a bonus. The design phase is therefore extremely important to the fundamental success of the arm, as the comprehensive initial design will hopefully reduce mistakes later in the process. The base of the robotic arm needs to act as an anchor for the whole device, whilst harbouring the electronics. The electronics included an Arduino board and a servo board, as well as the respective wires and power cables. The base should influence the centre of gravity so the system is stable. It needs to also contain a system that rotates the arm in the XY axis around a single vertical point. 2 single degree of freedom revolute joints will make up the shoulder joint of the device, allowing for internal or external arm rotation and flexion and extension. At this point in the design, I realized that I have no idea how to make a servo-powered joint. Looking at the biology of a human arm joint, the movement of the ulna and radius is created by muscle contraction and relaxation from the humerus and scapula. This creates an anchored body that controls the movement of the forearm. Understanding this configuration, the servo will be fixed in the preceding arm to the one that will move as a result of servo activation. So, imagining the components of the robotic arm are bones in a human body. For example, a servo will be placed at the bottom of the humerus and attached to and moving the ulna or radius. The fingers and wrist component of the robotic arm is the most complex, as hands typically have about 27 degrees of freedom, and the entire robotic system will only have about 5. However, I wanted to encapsulate at least 3 components of what the human hand can do. I wanted the robot to be able to grab, lift, and turn things over by rotating the wrist, as well as flexing and extending the wrist. In order to achieve this, we needed to design 2 components that could be manipulated in 3 directions. Having a pretty good idea of what I wanted to design, I then went into Fusion 360 and created a generic outline of what the arm configuration will look like. The design had no servo motor, size or functionality considerations, and was just made so I could wrap my head around each joint and what it was going to look like. From previously trying to design little machines, I now understand that despite considering every factor influencing the design you can think of, the only way to properly figure out a solution to them is to begin designing functional parts of the design and encounter the problems firsthand. So I decided now is the perfect time to begin designing each individual component of the arm in the CAD software. To begin the CAD modeling, I created an as accurate as possible model of each motorized component and began designing the arm components around them. The base component is made up of 3 separate parts: the frame, an Arduino, and a servo board holder, and a plate that holds a servo motor and leg supports. It is also designed to be fitted together with screws. Arguably, the most technically challenging design component was the shoulder joint. While rotation around a single point with swinging motion is theoretically straightforward, the attachment of 4 arm components introduces significant variation in the system's center of gravity and torque. This increases the overturning moment, which can exceed the resisting moment if the joint is merely resting on a surface. Therefore, the shoulder's rotational components needed to be securely fixed to the base to prevent toppling, while still allowing for controlled rotation. Additionally, care was taken to ensure servo wires could pass through freely without obstruction. For the next week or so, I continued with the CAD design. I made the decision that the other side of the joints from the servo connection would be designed to fit potentiometers. As they have low resistant rotation, they are lightweight and compact and can be used in the future to feed back the position of the joint, as the servo used in this project was unable to send position data. Symmetry through the entire design was really important to ensure each joint moved along a straight line and didn't introduce any unnecessary structural stress.
All right, we are at day 9 or 10 of the Robotic Arm project. Over the last 10 days, there's been a lot of CAD design, a lot of Amazon orders, which have arrived. We've got about 4 of these MG996R motors, one of these 20 kilo servo motors, and about 5 or 6 servo minis. They have all their attachments, and they're what we're going to use for the arm joints. In terms of the CAD design, we are at a point, I believe, that is a good starting point to make some refinements. We have the base, which is going to contain the servo motor, the Arduino, have power input, Arduino input, and it will also hold the 20 kilogram servo motor. That 20 kilogram servo motor will let the arm do medial and lateral rotation, kind of like this. It'll twist the arm that way. That is attached to a bicep section, which has a servo motor, which allows the biceps from the shoulder joint to do abduction and adduction. Moving up in the design to the forearm section, the lower servo motor will be in charge of flexion and extension of the elbow joint. The top servo motor will do medial and lateral rotation of the wrist or the hand. Then in the hand joint, we have a servo motor for flexion and extension of the hand. And then up here, we have one single servo mini motor, which will open and close pinch fingers. Some of the servo motor connections have been made to size, others have just been roughly done and a little bit off. So we're going to have to go through, finalize all those, make sure all of the things are millimeter perfect with a bit of leeway for 3D printing. Another error or another thing I'm not happy with is this bulky section between the forearm and the arm. I'm thinking that that's going to throw off its center of gravity. If we go and pick something up over here, it's just going to lift the whole base up and will fall over. So even though there's 2 servo motors in here in the forearm section, we're going to have to try and make that a bit smaller. There is a lot of mass out here, and this has a lot of unused space, so we'll try and fix that around and make it more streamlined and the distribution of weight a little bit better. So hopefully we can get that done in the next couple of days and start setting up the electronics of the whole device, making sure that these power to the Arduino and the power supply. Hopefully everything works.
I then started designing the controller for the robotic arm. It's not a perfect scale, more like a rough 1:3 scale, but close enough to do the job. Each joint on the controller uses a potentiometer, which acts as a position sensor. As I move a joint, the potentiometer's resistance changes, which the microcontroller reads as a voltage. That voltage gets mapped to a servo angle, allowing the robot arm to follow the movements in real time. So, in theory, every time I move a part of the controller, the robotic arm mirrors that movement almost instantly. It will hopefully be a really intuitive way to interact with the model. Finally, the CAD modeling was complete, and I decided to then spend about half a day rendering and animating the whole thing so I could envision what it was going to look like at each angle. If there was enough space between each part to allow for the complete range of motion, and then an animation of how each individual component would fit within the design. 3D printing was completed over the next week or so using the AnchorMake M5 printer, which worked perfectly when there was no user mistakes. In total for this project, there is 26 individually printed parts, and almost all of them had to be printed twice after realizing design errors after printing or printer setting mistakes as I learnt how to use the printer properly. Okay, we're now 38 days to the start of this project, and I think we are finally ready to start putting all the pieces together for the last time. There's been a couple of printing errors, design errors, but as a result, we have this cake tin of all the parts, the 3D printed parts, the potentiometers, servo motors, servo boards, Arduinos. All we've got to do is put it all together and hope that it works. Based on everything, it should work, but we'll just have to wait and see how we go.
We're about to do the final test.
The first trial with everything connected highlighted significant weaknesses in the software the Arduino Uno was running. However, it showed that mechanically and structurally it had the potential to work. Each piece showed signs of perfect functionality, and the passage for the wires didn't impede the arm's function. Looking further into the Arduino code, the strategy to send potentiometer signals to the servos by updating each servo one by one within individual limits was way too slow to reflect real-time potentiometer's positions. Averaging each limit of the potentiometer into a universal range and sending every potentiometer value each time drastically improved the system. The current state of this project accurately mirrors the potentiometer position in real time within the design limits without toppling over the machine or browning out the Arduino. There is, however, one really frustrating bug in the relationship between the wrist potentiometer and servo motor that would cause the system to brown out, which basically means the system would draw an uncomfortable amount of current from the Arduino and make it pause. This weird problem occurred only at a specific resistance value and persisted after changing potentiometers and Arduino boards. As a bypass, the button on top of the model can be pressed twice to oscillate the wrist joint. The functions of the arm include a single press of the button to open and close the claw. The claw is also a weak point in the design, as the point of contact from the servo motor attachments is too far from the sliding guide center point, which consequently pushes the claws diagonally along the slide, increasing the friction and causing it to jam. This can be solved by using a very loose rubber band, but then the band is not strong enough to grip objects properly. Pushing the button twice oscillates the hand at the wrist joint as mentioned, and also pressing the button 3 times sends the arm into playback mode, which listens to the potentiometers without moving for 10 seconds, and then after that plays back the moves. After its performance is done, it automatically returns to normal mode, mirroring the potentiometers. A simple user interface is created through the use of the button and a blue LED. I think this project has been a big success for my first shot at it. It has the ability to be controlled manually by the model, but it also has the potential to be controlled by a Bluetooth chip or EMG signals thanks to the Arduino board. I have learnt so much throughout this entire process, and if you have any questions, please ask them in the comments below. I've also left a detailed description below with all the parts and links to where to buy everything, as well as my Arduino code. I really hope you enjoyed. Thanks for watching.